Hey all, I wanted to do a quick video here as a follow-up to my earlier series on making this little buck regulator here that I did a series on the whole design and manufacturing of it. And I want to do a quick follow-up in terms of letting you be able to calculate the efficiency of this thing. I mentioned in the earlier video that buck regulators or switching regulators in general are usually significantly more efficient than a standard linear type regulator. So I wanted to give you an opportunity to see how you would go about actually measuring that and confirming that for yourself. So in this case, I've got one of my buck regulators here, and I've got a whole pile of wires and meters hooked up. But in summary, what's going on is that these 2 meters over here, they're measuring the input to the regulator over here, and then these 2 meters over here, if I can get the glare off, are measuring the output here. And so what's happening is that I've got my bench power supply, and in theory I could use the meters here in the bench power supply, but they're just not super accurate. And so I've got a couple of extra multimeters here that I've got measuring the input voltage and the input current. And so we've got those hooked up here on the input. One of the the current one is obviously in the line in series with the input here, and then our voltage is across the line measuring the input voltage. And just so you know, I am measuring actually the input voltage after this meter, so any losses in the resistance bridge in this meter aren't a factor in this. It's not going to be perfectly accurate. These aren't super fancy meters. But so that's preferable anyway. And then the same thing is happening over here on our output. We've got a meter on the output measuring the voltage, and then the leads coming off here, going down to a load resistor, which I'll change out. I've got a couple of them, and then going through our current sense meter here to see how much current's going through, and so we can compare the input current and voltage to the output current and voltage. And so with our standard equations of V equals IR, Ohm's law, and P equals IV, or our calculating watts, we can figure out what the efficiencies are when we look at our input voltage and current and our output voltage and current, and compare, do some math and figure out what that is. And so what I'm going to do here is that instead of making this video super long, is I'll go through and I'll take these extra load resistors here and I'll flip them in. So right now I've got 100 ohm, is I'll do 150 ohm, and then I'll do 250 ohms to make a 25 ohm. And I'll take all these measurements here and I'll dump them just quickly into an Excel spreadsheet, and then we'll jump over to the computer and I'll show you how we take that just that raw data, we'll throw in some formulas and actually calculate these values and see at these load resistances what the efficiency is of this particular buck regulator. We'll also, for the heck of it, also adjust the input voltage here. Right now it's at about 9 volts. I'll bump that up to, I don't know, I'll try 12 volts, and then I'll drop it down to, I'll try 7 volts. And so we'll get a couple of input voltages as well, and that'll probably affect our efficiency as well a little bit. So we'll take a look there. I'll dump those into the spreadsheet, and then we can follow up there just after the magic edit jump, and so we'll see what the efficiencies are. All right, so we've finished doing the load tests with the various resistors, and so now we've dumped these into, I just use LibreOffice, but some sort of Excel spreadsheet type thing. And so we've got our 3 different input voltages. So we did one at 9 volts, one at 7 volts, and one at 12 volts. And then our 3 different load resistor values at each level. And so, like I mentioned earlier, we've got multimeters on the input voltage and current, and then meters on the output voltage and current. And so then we'll calculate what the input power is, the output power is, and then what our efficiencies are. And one thing I wanted to note as well is that these values are going to include the quiescent current, the current of the device itself just sitting there running. I took these values just once at each voltage with no load, and this is going to handle any overhead in the converter chip itself, as well as the little status power LED on there. So we've got 4 milliamps, 5 milliamps, and 3 milliamps at these voltage levels, and so you can see that it uses a little bit less current at a higher voltage, because in theory the power will remain relatively constant. It's going to change a bit, but so as your voltage goes up, your current will go down because your power will remain the same, and your power equals your current times your voltage. And so I've got these two equations here just written out here for everyone's fancy reference. So what we'll do here is that we'll start with our input power, and so we'll just do a quick equation here, is C2 times B2, and so that's going to be our input power for this value here, and we'll just expand this through, and so delete these zero values where they don't apply. And so we can see here that we're about a third of a watt, about half a watt, and about 1 watt of input power. And then we'll go over here and do the same sort of deal. Let's do equals G2 times F2 and get our output power in wattage. And again, go and remove these. And so we can see here also that these are somewhat more round values because our output voltage is regulated. It's stuck at exactly 5 volts. And so our output current, as we switch those resistors out, the resistance of those resistors isn't changing. And so because the voltage is always the same, the output current is always the same, and then the output power is the same amongst these as well. And so what we're really doing is comparing these against our input voltages and powers to generate what the losses are. And so, for power loss, we can do, real quick and simple is we're going to be CD2 minus H2. And so we've lost 63 milliwatts, because these two columns are in watts, and so we can expand this down. All right, and then dump our values here. And so we can see how much wattage we're losing at each level here. And so we can also see that it looks like the most efficient one, without having actually calculated the percent efficiency, looks to be our 7-volt range, because our power loss is the lowest amongst any of the groups. And so what I'll do here is do the same sort of deal and we'll just put this in a percent sort of time frame. So we'll go over 100. There we go. Sorry, I had that backwards. And then we'll expand this. And so now we have our efficiency values here. So we're at 79.89%, 83, 87% efficiency, 83, 86, 89, 77, 81, 85% efficiency. So one, we can see that in general we're most efficient at this 7-volt input voltage range. And then two, we're also finding that overall the converter is more efficient at a higher load. And I expect that at some point that certainly will taper off. But at the current loads where we've been testing at, i.e. 50 milliamps, 100 milliamps, and 200 approximately milliamps, we find that in each range we're also most efficient there at our higher load values. And so this is a real quick and easy way to actually, and this is this is the truthful way of how you're going to go about calculating what the efficiencies are of any regulator that you're using. And these same methods will apply exactly to any regulator. So like I was mentioning earlier, how a linear regulator is going to be significantly less efficient. Um, that's this same test setup. If you take a standard 7805 linear 5-volt regulator and do the same test, it will apply exactly, and you'll get different values here for your efficiency, presumably much lower. The biggest difference there is that it's going to be based primarily on the input voltage over here. And while this does have some impact over here, these are all in the approximately 80s to maybe hitting close to 90 range. As you go up in input voltage, linear regulators have to burn off more and more, and so the higher you go, one, you'll notice the hotter they get, and that's because they're having to burn off more of that input power to get that same output power. So that's what you're looking at there when you're looking at a linear regulator, and so you can do that test yourself. But this is the test setup, and like I showed earlier in the film footage, is that you can do it with just 2 multimeters. I happen to have 4 laying around, so I set up all 4. But if you've only got 2, and even if you don't have a bench power supply with meters built into it, if you expect your output voltage to be constant, and if your output voltage is constant and your output current is going to be based on your output voltage, and you can independently verify that by switching your configuration around. But you can put your 2 meters on your input side and just expect that these will be the same. And so, and that again, you should verify that, and do spot checks. But that's a good way to get by with 2 meters and not having to have all 4 hooked up. All 4 does make it quicker, and I'm also not saying by any means that these are super fancy, super accurate meters. My fluke meters, certainly the best of the bunch there. But they're accurate enough to get a general idea of what this is going to look like. And like I said, this efficiency value is taking into account, because these input current values take into account the input current required by the device itself to run, with no load. So, you could, in theory, take this value and calculate it out to figure out what the quote unquote conversion efficiency is. But that's not going to be an accurate representation of what you're going to see in the real world when using this device. And so that's why I mark it here, but we're not going to actually take any time to calculate those different values, because they have no real applicability. Is that they would inflate these numbers. If we took this out, these numbers would get better. They'd go higher efficiency, but that's not real. So we'll leave those out and just mark those for reference, and that there is some current that the device itself uses, for the LED, for the converter chip that sits there while it's running. But so that's how you do it, and quick Excel spreadsheet to calculate that, and then you can of course take more measurements at more load values, and then take your efficiency values and plot them on a nice chart, and do any sort of fancier analytics or display methods that you so choose. Anyway, thanks for following along, and hope you enjoyed that, and you learned something.